Okay, so I'm going to kind of quickly go over the highlights of Chapter 1 in your textbook. Not going to cover everything in the textbook. It's a nice read. Please read it. And then at the end of this, near the end of this PowerPoint, I'll tell you what the homework is. So be sure and stick all the way through the PowerPoint, unlike some of you did with YouTube's last week. Did not go all the way to the end. So anyway, Chapter 1, one of the important aspects that every first programming book will talk about is how a computer is organized. To many of you, this is going to be old hat, but we'll do it anyway. We'll go over it because it's in your textbook. So let me get my pen here going. So computer is composed of these basic parts. The center of the computer, the heart, the brain of the computer is the CPU, which means Central Processing Unit. It may also have an ALU, it does always nowadays, which is an arithmetic logic unit, does calculations for you. So the input, the brain to your computer, there's something like here's a microprocessor altogether, Core i5. You have to have inputs to the microprocessor and outputs to the microprocessor. Inputs are typically keyboards, mouse, audio signal. Something will be processed by the input will get processed with the CPU, and something will be output, maybe output to your monitor, output to your speaker, printer. But also the CPU must interface with internal memory in the computer. This is your RAM. External memory, this is your thumb drive, CD drive, whatever external memory you have. So from a software point of view, though, the software builds up in layers. So at the very center of your computer, at your CPU, is the hardware. So whatever your computer system is, it will have some sort of microprocessor inside and some sort of memory. The lowest level to talk to this hardware, to this electronics in here, is assembly language programming. So assembly language code can talk directly to the hardware inside your computer. It is very close to what we call machine language. Machine language is literally the ones and zeros that are stored in your computer and in memory. But it's not literally ones and zeros, it's actually transistors that are turned off or turned on. That's how it makes a 1 or a 0. So assembly language is very low-level programming, and I'll show you an example here in a moment. The next layer here shown is where your operating system resides. This is a higher level of programming. It's more human readable. Assembly language is not very human readable, and machine language is not really readable at all. I'll show you an example. So we have your operating system, whether it's Windows, Linux, Unix, whoever. That's the next layer of software that's closest to communicating with the hardware. Then we have our applications. So applications are not programming languages. They are like your Word, your spreadsheet, your Excel. An application is also a compiler. You use a compiler to convert your source code into machine language. And then the last layer, of course, is the human user out here. So just to give you an example, this right here is assembly language, or how assembly language looks like if we try to write it down. So I'm not assembly language, machine language. This is machine language. Machine language is a sequence of ones and zeros. Zeros are a transistor turned off somewhere inside your hardware, and ones are some transistor turned on somewhere in your hardware. But we can't read a series of ones and zeros at all, so we usually convert our binary language into hexadecimal language. So this is actually in hexadecimal, which is a little bit easier to read. In this class we don't go over binary to hex to assembly language programming. That's done in a different course. But anyway, that's what machine language looks like. The next layer here would be your assembly language. So an instruction like move left here is moving some values between registers. Registers are locations in memory in the computer, or locations of storage inside the microprocessor. But this mnemonic, it's called a mnemonic, will translate directly into ones and zeros if you break it down. The mnemonic just makes it easier for us humans to read. So this is actually very, very close to machine language. The next higher level of language is something that's more human readable. This is an example that looks like either a C language, a C, C sharp, C++. This is where we're going to be working. So a variable that we define, such as count, and defining a variable, this code can be turned into something like this, and then this code right here can be turned into something like this. During the course of this semester, I will actually give you an example of doing that. So we're going to work at a high-level language. C is a high-level language, but it is not a very high-level language. Some languages that are higher would be like Python, C Sharp, and C++. They're a higher-level language than core C is. So this is also an important drawing that's in your textbook in Chapter 1, talking about how a program is compiled, linked, and executed from sort of a high level. You did that this week when you did the Hello World, just to make sure that you had everything installed correctly. But basically you start with a C language program. This is your source code, something that you've written in Notepad++ or Notepad or Visual Studio or Vim or some kind of an editor. You've written human readable C language program. The file ends with a .c extension. So this is, you write it in some kind of an application. Computer doesn't know what to do with it at this point. It's just text. So you have to compile it. Compiling is turning your program into machine language, that series of ones and zeros or transistors that are on and off in memory somewhere. So when we compile, we use our GCC compiler. When we compile the program, it's converted into machine language and stored somewhere inside the computer. So now we have a machine language program. It looks like this, ones and zeros, ones and zeros. When it's machine language, this is what we call our object code. So we have our source code here. We compile, it turns into object code. But that's not enough yet for the program to run. The program also has to be linked to other machine language statements so that it will work correctly. The linking process, for example, can link to our include standard I/O statement. This allows us to write to the monitor or get input from the keyboard. So finally, after it's linked, the program is then loaded into, the completed program is loaded to someplace in memory, so that when the CPU calls the program, it can be executed. So then now we have our executable file. At the end of Chapter 1, there's an important example about the process that you should use to solve engineering problems, in particular engineering problems that have a programming solution, a programming-based solution. So I will go over this process that your textbook asks you to use, and I will say that as being an engineer my whole life, this process is very standard, and skipping steps usually makes you go in circles when you're trying to solve a problem. So if you follow these steps, you will be much more successful in reaching some kind of a solution or processing your data in the real world. So, oops. So number one step is state the problem clearly. I cannot overemphasize this enough. If you do not have a clear mental picture of what the problem is that you are going to try to solve, you are going to have great difficulty solving your problem. So after you state the problem clearly, describe the input and output information. What are the input variables? What output quantity are you looking for? Very important step number 3, work the problem by hand with simple data. Just test yourself. See, is what I think this problem doing makes sense? Can I solve it on a piece of paper with simple numbers before I have to process a whole bunch of data with my relationships? Then finally, you're in a position to develop your solution and convert it into a computer program. Developing your solution means developing an algorithm. It means deciding how your program flows. What are your inputs? What are your outputs? What process do you have to do in between? It may involve a flow chart. We haven't really addressed flow charts yet, but they are a very useful tool for mapping out what your algorithm has to do. And finally, after you have your solution and you have a working program, you need to test it with a variety of data. Even if you are a programmer in the video game industry, for example, before a game gets released onto the market, it spends time with beta testers, and beta testers find problems with the program. So this is a form of finding problems with your program, testing it with a variety of data. So let's go through an example. This is the example in your textbook, but I will elaborate on it a little bit. And this particular program is going to be used right away in Chapter 2 as we go more in depth with the details of C language programming. So step 1 is to state the problem clearly. So our problem is to compute the straight line distance between 2 points. Now, to make sure you understand the problem, I suggest drawing a picture. A picture is worth 1,000 words when it comes to making sure that you clearly understand the problem. So we can choose 2 arbitrary points in the XY coordinate system. So 2 points have been chosen here, and we draw a picture and say, I want to compute the distance between 2 points, arbitrary points. Step 2, define what your input and output parameters are. My input is this point, so I could call it point 1, point 2. And what do I want my program to output? I want my program to output the distance between those 2 points. Right here is my program, some algorithm that computes the distance and then says output it to wherever it needs to output to, a file, the monitor, wherever. So step 3 says do a hand example. Nothing wrong with doing a hand example, and I will walk through that. Some of you have very strong math skills. Some of you in this class do not have as strong of math skills. So, that's why I further think it's worthwhile to go over the hand example. I haven't read your survey results yet, which I will be doing this weekend, and I will see what everybody says their math level is. So I know whether I have to do the math examples first before we do the programs or not. So we'll see. Okay, so I have a hand example, and for me, a picture is worth 1,000 words. I love to make hand examples. This is point x1, y1 arbitrarily. This is a point x2, y2, x, y. And since we will do an example with simple numbers, I'm going to say that this point is 4, 7, and this point right here is 1, 5. I want to compute the straight line distance between these 2 points. That's that right there, straight line distance. So that's what we want to find. So how would you do that? So just recalling from probably algebra, I have a x distance right here, and I have a y distance right here. And when I figure out these distances, this x distance and this y distance, then I can use the Pythagorean theorem and compute the distance between the 2 points. So this symbol right here, this is called a delta. It means change in. So in this case, it's a change in x. So delta x equals x2 minus x1. So this distance right here, this x distance right here, is 4 minus 1. This y distance right here, if this point is at y equals 7, this point is at y equals 5. The y distance, which is also the length of this side of this triangle, the y distance is y2 minus y1, 7 minus 5, which equals 2. And Pythagorean theorem, oh, I should have checked the spelling. That doesn't look right. Says the distance between those 2 points, or actually the hypotenuse of the triangle that we just drew, is x2 minus x1 squared plus y2 minus y1 squared So if I do my simple hand example, I came up with 4 minus 1 squared plus 7 minus 2 squared, which equals square root of 3 squared plus 7 minus 5, sorry, plus 2 squared, which is the square root of 13. Distance equals 13. So when I did this problem, I actually defined now what the inputs are. My inputs, there's actually 4 inputs. Inputs to my program should be x1, x2, y1, and y2. And my output to my program is distance, d. I can call it d. So here, let's take a look at the solution in the program. No, step 4, sorry. Step 4 says develop the solution and write the program. So the solution is defining the inputs, computing the length, and outputting the distance. Print it to the screen, print it to a paper, print it to a file, whatever we decide to do. So here's the solution. This is also in your textbook, but I am going to go ahead and walk you through the solution just one time real quickly, because I want to point out some things not so nice about the solution and some things that are more nice about the solution. I'm going to go out of PowerPoint. Before I do that, I'm going to go ahead one slide, because we're going to test this. We're going to look at the program, test it with a variety of data, which is the 5th step in the process, to feel comfortable that our program works as we want it to. This is where I point out that the program doesn't exactly work the way I want it to, leaves room for improvement, but we shall see in a moment. Before I go to the example, your homework for this chapter is to review the review problems 1 through 50 at the end of chapter 1. You are responsible for all of that material, those questions, on a future test. The midterm is probably a in part multiple choice and in part take-home programming midterm. But the answers to all of these questions are in the back of your book. So you can ignore me if you want, but I really suggest that it is good for you to go through the questions and make sure that you can answer them and that you understand them. So quiz yourself. I will not give you a grade for it, but you're responsible for the material. Okay, so let's do here's the program typed up in Notepad++. You can see here is where the input and output variables are declared. We're going to talk about this a lot more in chapter 2. It does some calculations. It computes the distance, the square root of side 1 squared plus side 2 squared. There was a more efficient way to do this, but this is the example that you're given in the textbook. Then it prints the result to the screen, and we will also learn about this statement going forward. The get character statement right here, this is a method, is telling the program to sit and wait for a user input. Otherwise the program executes and closes, and it flashes by so fast that you can't see it. So there's the program all typed up. I've already compiled it. Here it is compiled. I can run it from the command prompt window or the PowerShell window. I can also run it by double-clicking on the executable icon in the GUI-based environment. So I will do that. I ran it. It says the distance is 3.61, which, yes, that is the square root of 13. Cursor is flashing because it's waiting for an input from me. So I touch any key, enter, and close, and the program closes. Problem with this program is these values are fixed. So if I wanted to repeatedly compute distances between 2 points, I would have to type in new values here and recompile the program and run the program. So this program to me is not very well written. It doesn't really serve my purpose. I would improve upon it in the next iteration.